So yeah, today I'd like to talk about my PhD thesis, Advances in Technology Evaluation and Decision Support Studies using Bioeconomic Farm Models. So just like Francisco just said, I finished the PhD last year. So some of you might think, okay, wow, this guy was fast when he was a PhenoRob PhD, and that's because I cheated actually. PhenoRob is actually, I switched projects in like half of the PhD time. So I already had a start advantage. So that's why it may seem like I was early, but actually I took the quite regular, I think, 4 years for the PhD. Yeah, but more to that later. So for most of you, I think you have a more technical, or you might have a more technical background, and you might not have an economic background, and you're probably wondering, okay, that's a lot of, that's a big title, it's probably doesn't tell me much. So probably let's just have a more of a look what does, especially bioeconomic model, what does that actually mean? So bioeconomic models are just a simplified illustration of the interrelationships on a farm. So on the farm, we have biophysical relationships like, okay, how does a crop grow? If I apply fertilizer, what effect does it have? If I feed cattle with different feeds, how does it affect its growth? And then we also have mathematical formulas. So that's put into mathematical formulas. Many of you, I mean, you probably, you already work with these kind of models, especially in the biophysical part. But then we also have the economic part where you say, okay, for instance, I was just talking about the cash crops. If you apply fertilizer, that has a cost of X, but I can sell the crop for a price of Y. What is now the optimum level of fertilizer where applying an additional unit of fertilizer still gives me more economic return than the price I paid for the fertilizer? So these bioeconomic models, they kind of combine the two, so the biophysical and the economic part, and enable an economic optimization of a farm. So usually there's two applications of these. So on the one hand, we have the opportunity with these models to show the most cost-effective adaptation strategy to new policies. So interestingly, these models are often used for policy evaluation, where policymakers, with my current employer, the Thünen Institute, we are a federal research agency, just like probably with Corona, many of you have heard of the Robert Koch Institute. So kind of like, these questions more to an agriculture, so not Corona, but any governmental question that goes into agriculture department, that is usually first answered by the Thünen Institute. So and so when there's a new agriculture policy, often we at the Thünen Institute, we get asked, okay, how would that policy affect, or what is the most likely outcome for farmers or for a whole region, for, let's say, whole Germany? And so these models are used for that. And then also these models can be used to show whether a new technology, and that's why it's also applicable for PhenoRob, is for a farmer, is profitable, or for a region, what does influence could it have on a region? So we could also use it for that. As I said already, we have, we have two mainly use cases for those, so the policy and technology, which I just talked about, but we also have a different one. We have the decision support system. So also farmers could use these kind of models, and also consultants saying, okay, if I have a very specific farm setting, and now I have the option, let's say, to buy a robot, should I, for my very specific farm, do it or not? And so that's the other. So these are basically the two main use cases for the bioeconomic models. And interestingly, especially the latter part is rarely used. So that's something that, I come from. I have a farm background, so that's always been of interest to me, studying economics in the master. Also in the bachelor, I was thinking, okay, why are these models, they're existent, we use them for policy evaluation, but we rarely use them for decision support. So even though it should be interesting for farmers, and one reason that's given in research why this doesn't happen so much is because often it's stated that for farms the data requirements are very high. So if we, let's say, look at a whole region, we can just use aggregate data from official statistics, but for a single farm, we need a lot of data. And the more complex the policies become, the more complex the technologies become, the more data we need. Okay, so and that's why yeah, that's why now with new data that's been coming up, we have especially through the digitization, we have access, especially on farms, with high resolution data, such as plot geometries and soil and crop data, which is now also publicly available. So, and this allows, on the one hand, expanding existing models for evaluating new technologies like the PhenoRob robots or policies, let's say, and that's also interesting in the PhenoRob context, the EU policy of kind of forbidding more and more pesticides and herbicides. So that's also implicitly fostering new robots and new technologies. And on the other hand, it allows us to develop better or also novel decision support systems that can be used on farms. So that was the overarching, or let's say the background that kind of led to the PhD thesis. So I knew I wanted to work with these economic models. I also knew that I really wanted to get a deeper insight into the decision support aspect of these models. But also, and that's especially due to my first project that I was employed with, it was a beef project called Sustain Beef, where the overarching goal was to see how the beef production sector in the EU could maybe make it a little more sustainable. And so essentially the PhD then, with this background and of the two projects, it actually consisted of the following 4 papers. So the first paper, which essentially was discussing the economic use of crossbreeding and sex semen in Holstein dairy herds. So that's oddly specific, I know, but that's just because the project was about that. So for those of you who don't know what both crossbreeding and sex semen is, so let's start with the sex semen. That's especially that's especially interesting because with cattle breeding, it's possible to split the female and male semen before artificially inseminating a dairy cow. And especially in the dairy milk production, the male cattle is not really wanted and doesn't have any economic viable aspect. So just like you probably heard of male chicken that gets shredded because there's no economic value to it, we similarly have a lesser known issue in the dairy sector. So with the crossbreeding, with the sex semen, it's possible to essentially say, when artificially inseminating a cow, okay, I want this calf to definitely be a female calf. And that's possible with the sex semen. And on the other hand, we have the crossbreeding. So the crossbreeding says we have different breeds. Basically, for instance, the Holstein breed. So it's a very high yielding dairy breed. But then we might also have a different breed, which is high yielding in for instance, meat production. So when crossbreeding, we're using the heterosis effect. So we're basically maxing out on either of these properties of the actual breed. And that's especially viable for if you have, let's say, a cow which is very old, and so you don't want to use its offspring for your remontation of the new herd, but you actually still don't want to give up on that cow. So that's what the crossbreeding is for. So we can prolong the lifespan and therefore reduce or increase the sustainability of the system. So essentially, that was technology assessment of an existing in an existing model. We used the model farmed-in for this. Don't want to go into the details here. Then the second paper, so completely different topic, was the Fruchtfolge. So we're going to talk about that in the section for a little longer. So there was a decision support system to optimize cropping decisions. So that's already been introduced in the PhenoRob context as well. So that was the first PhenoRob paper in that sense. So yeah, here was development of a novel decision support system where farmers could themselves evaluate policy impact assess or create a policy impact assessment. And then we had as a third paper the creation of a synthetic farm population for North Rhine-Westphalia. Here the background was that Fruchtfolge is an on-farm, a single farm optimization model, which requires a lot of data. We'll get to that in a second. And the issue was that there was no public data set that gave us a resolution that we needed to scale up this system for, let's say, the whole federal state, for instance, of North Rhine-Westphalia, or even whole of Germany. So with different public data sources, we tried to create this. So the outcome was just the creation of a high resolution farm population. And then we had the last paper, the single plots or shares of or area shares, how the representation of cultivation decisions in bioeconomic farm models influences the simulation results. And that paper is basically just making a difference between the model I used in the first paper, so FarmDin, which due to the data availability back then was looking at the farm as an aggregate, just like considering, okay, all the single plots that we have on a farm, we just assume that's like one big chunk that we can just split indefinitely. And Fruchtfolge, on the other hand, looks at specific plots and with all its plot characteristics. So, and I wanted to see if we put that into an optimization model, how does it affect the optimization results? If we, on the one hand, have the assumption we're just looking at this at a big chunk, or if we really look at the individual plots, so basically the decision level the farmers really have. So that was the analysis of how that level of detail affects the simulation results. So let's first look at the Fruchtfolge decision support system. So from its objectives, the idea was to develop a decision support system to optimize cropping decisions and fertilizer planning. So the resolution of the model, which will be important throughout the whole thesis, was the single field or plot level. And what's important to me was that we have automated data collection. So the connection to existing research is, especially that we are using the concept of user-centered design. So here, the idea was that we really just look, instead of like the traditional approach, where often we as researchers think, okay, what do I think is the issue? Is more, we ask farmers in this case, also the actual users, what is your main issue? And then try to build the application from that point on. So the application of the final product or of the decision support system is mainly a decision support system. It can, however, also be used for policy and technology evaluation, which has also been done in the later papers. So from the structure, it's built like a classical web app. You have a login section. Then farmers enter their ISCS number. So some of you may know the INVECOS. So every farmer in Europe, most of the farmers in Europe, they apply for the subsidies that are given out by the AACS. And within that subsidy program, they also have to fill in which crops they grow on which field, or with what they did in the past. So when we get the number and that PIN, we can automatically basically gather all this data from that database, but we can also acquire additional data. Since we now know which plots the farm cultivates on, we can get more data on the gross margins or the assumed gross margins we have in this region. We can get automatic data on soil types and soil qualities. We can get the farm field distances from the OpenStreetMap routing machine, and a little more data. So we can all put that together and then automatically create a model for the farms and then optimize that. And the idea of Fruchtfolge is basically to, farmers log in, data is collected automatically. There's an optimized cropping plan presented, but that's not supposed to be the final point. So idea was that farmers now look at this and then iterate. They say, okay, well, this assumption is bad. I want to change that assumption. So they go back, change it, and then re-optimize. And, so it's basically a cycle. Exactly. So, and then from these, there's been a couple of open source software projects that's been given out, because when developing this, I was kind of, sad to see that there's been a lot of effort ongoing with many companies, especially writing always the same kind of components over and over again, because they're not willing to share. And I think it's especially us as research organization, if you have an idea for, you know, I don't know, let's say you do some segmentation of satellite imagery, and you do, I don't know, let's say you do some analysis on NDVI, and now let's say you want to try it in practice in a survey. You often need farmers to input their fields, and I realized that this is something, you know, that takes a lot of time often to program in a good way. That's so usually you can always throw something out which is quickly done, but then most of the farmers will have trouble to upload their data which is already existing. So that's why I spend a lot of time trying to open sourcing these single components, so everyone can just use that for future research, or even commercially if there's a use case in commercial environments. So from the structure, the result section of Fruchtfolge looks like this. You have kind of like a table where every single field is listed. You can see how big the field is, how far it is away from the farm, what crops have been grown in the past, and then also what is now the optimization is kind of giving you as a planning option for the future. Then in the second panel, we have kind of a chart, pie chart, which just gives an overview of like the crop shares we would see. And then down at the third part, we see difference to the optimum. So like the idea was that farmers in the table, they can just select different crops for a plot. If they say, no, I don't like this optimization or like the suggestion which was made by the optimization, and they can instantly then see why the optimizer didn't choose that option, usually because it was just not giving, it was just giving less money. Or sometimes it also violates some of the policies like agri-environmental policy, or some constraints the farmers set themselves, like, okay, the workload threshold would be exceeded if you do this. So the idea was to give farmers the the possibility to now make an informed decision, so they can themselves decide, okay, we're now deviating these kind of constraints, or deviating from the constraints we set earlier. Is that okay for me? Like, I'm now exceeding the workload threshold, let's say for September. Now they can decide, is that fine by me or not? So they can now even adjust the assumption and so on. Down in the fourth panel, we see the working time requirement of the current cropping plan. And at the bottom, we can also see a map, once again, where the plots are located and with the different cultures that are supposed to be cultivated there. In the paper, we also did a case study, just very, very basic example. We took a farm from the Balkan region, which is close to the Dutch border. And that farm in the Balkan region, we have a lot of so-called red areas. So in red areas are areas where the government said, okay, here's a lot of over-fertilization happened here in the past. Here we need to reduce the nitrogen fertilization by at least 20%. So, and that has an effect on the yields, obviously, and also on the maximum manure quantity that can be put on those fields. And especially in the Balkan region, the reason why there's such a, in the past, there's been such an over-fertilization is because there's a lot of animals in the region. So our assumption was we have a farm with 100 hectares of arable land and 2,000 pig fattening places. And so there was this new fertilizer ordinance that was just in place when we published the paper in 2020. And also autumn fertilization in that area was then not permitted. And the aim of the case study was then to show the economic saving potential that could, for that particular farm when applying the Fruchtfolge decision support system. Here we see the plots that farm operates on. In the left bottom, we see the farm location. Here in the first scenario, we have 0% of the plots in the red area. Then in the second scenario, we had 50% of the plots in the red area. And then we had a third scenario where all of the plots were in the red area. I think the 50% scenario was I think that's the reality essentially. So that's the line where really the red area goes through. And so those other two were just assumption. So, and then as a result, so we had basically as a reference in the old policy, the farm would make around 90,000 euro as a total gross margin. And then under the just optimization, optimizing the fertilization, but not changing the crop rotation at all, we could see that in the when 0% of the fields were in the red area, we could see that the profit dropped just by a little, and you see that it's dropping by up to 15% if like all of the fields are in the red area. And then if we allow Fruchtfolge to make an optimization, so to basically adjust the crop rotation accordingly and also to move the fertilization to different parts and different crops, we could actually regain 5% of the profit. So so that was basically the economic benefit of just using the Fruchtfolge application for that specific farm. So, and you see that's up to something, right? So if like the farm has 0% of the fields, we can barely see there is a minimal economic gain from using Fruchtfolge, but it's not as much as farms, obviously, who have especially like all of their fields in the red area. So now going off to the second paper, the farm population. So as I already said earlier, the farm population is necessary for use in technology and policy impact assessments. So like saying, okay, like we just had the example of the new fertilization ordinance, which was put into place 2020. So for these kind of things, it's obviously not enough to just look at one farm, which is for a decision support system. If it works for one farm, that's fine. That can be enough. But like for like policy assessment, we at least need to see, okay, what type of farms are affected, what regions are affected. So in order to do that, and especially with the fertilization ordinance, we had the issue that it was really on the single plot level, whether like a farm has plots within the red area or not. So like these old models, which were just looking at aggregates, they couldn't really capture the decision problems farmers were facing. So and that's why we really now needed a data set which was high enough in accuracy to be used in models like Fruchtfolge. Yeah, so that was our aim, to create a synthetic farm population for North Rhine-Westphalia with assigned plots. So synthetic means kind of we wanted to have the properties of like the real farm population of North Rhine-Westphalia with real characteristics regarding to like farm to field distances, overall farm size, animal size, and so on. But it should not be the true real farms, because that would be a violation against data protection issues. So that was really difficult to navigate, like what can we do without violating data protection laws, but also to be as realistic as possible. So what we did essentially was, it was a three-step program. So first we looked at the official farm structure survey, which everybody can look at. That's given out by the government. So that kind of says for the different communities. Okay, we have, for instance, farms specialized in pig production between 0 and 10 hectares in the community of Merzenich. There are 2 of those. And there's 5 farms between 10 and 20 hectares that are also specialized in pig production. And so you get essentially, you get the point. So we use that, and we also use the so-called farm typology of Kuhn et al. So Till Kuhn and David Schäfer, those are colleagues of ours. They once went to the Statistische Landesamt in Bonn, actually. So there you have to give away your phone and everything. You basically have to enter the room without any electronic devices, and then you're allowed to look at the true farm characteristics. So there in that room, they kind of made a typology. So they were looking what are the most frequent farms within a municipality and what characteristics that do they have. So, and then they talked to the statistics office what kind of info they can later on also publish. So that was a data source we used to basically together with the farm structure survey to make it a little more detailed. And then we added plots. So since we now knew, okay, there is, for instance, a farm with a category 512, that means it's specialized in pig fattening production. It has The size that was due to the farm typology gives us a normal distribution of like min, max farm sizes, standard deviation, and so on. So from that we sampled the number of farms within a municipality, for instance, and then we assigned random plots so that under the condition that the farm size is not or is met quite good, and then also depending on the specialization that the crop shares somewhat fit. So and then for like the problem, and then we actually used that in the final paper, the level of detail of the cultivation decision. So here we see an example. I already told you that like in the older models or the existing models, we had the issue that often due to the lack of data, we had to assume like there's a farm that has 193 hectare, and let's say there's a second farm which has 55 hectare. And all we knew was, okay, this farm is this big, but we didn't know the single plots, where they're located, what the soil properties are, what the soil qualities are. And below in the bottom picture, you can see the actual plots of that 193 hectare farm, and we can see actually like the distribution of the plot sizes and the farm to field distances and so on. And the question was, if we just look at the aggregate and then use our optimization model saying, okay, you can grow wheat, which gives you this gross margin, you can grow barley, gives you this gross margin. And then at the below, if we really, in the picture below, if we really look at the single plots and also put that into the model, would that give the same results? Or if that gives different results, how big are the differences? So that was the main point, or the main research question we wanted to answer with the last paper. Just in detail looking at these, I just described those. So like the first farm, like in the aggregate approach, we would just say, okay, it's the driving distance on average is 95 kilometers. Soil quality is on average 92 is the soil quality rating, and the plot size on average is 4.2 hectares. And you see for yourself, so in the bottom pic, or the top bottom right picture, we have the actual distributions. And we can see, for instance, that the driving distances are more skewed to the left, same with the plot sizes. And so also with the soil qualities, we have very few outliers. So then we were looking at different, or from the methodology point, we were looking at different levels of detail. So in the single approach, kind of like like how the decision problem is actually looking for, like for farmers, they actually have to decide on every single field what they grow. So that actually accounts for the spatial distribution of the farm's plots, also accounts for the individual plot characteristics. Like a farmer would probably say, oh, those far distant fields, I can't cultivate potatoes there because potatoes contain a lot of water. So that's a lot of transport costs I'm facing there. So they probably wouldn't do it. Or let's say the soil quality on some other plot is too bad for a certain crop, so they wouldn't grow it there. So that's all making it more complex, and that requires the use of binary variables for so basically mixed integer linear programming or even non-linear programming, which making it from a mathematical point of view a lot more complex to solve these kind of problems, because we don't want to arbitrarily split plots because farmers for a certain reason actually chose to cultivate the plot like it is. Then as a middle kind of approach, we chose the categorized, is what we call it, that aggregates plots by one or more categories. In the literature, what we sometimes see is that here like categories like good soil, bad soil are chosen. It's rarely done in the literature, but that's the only other approach we could see, we could find. And then often farm or regional average plot characteristics for each category group are reflected in the bioeconomic farm model. And then at last, we have the aggregate approach, which in our literature research is the most frequent approach, that aggregates all of the farm's plots and also aggregates all of the farm characteristics. In our paper, we've been very fair, and we've also really aggregated all farm characteristics like soil types and so on. In the literature, we actually rarely find this. In the literature, often there's been just made assumptions like the farm distance is always 2 kilometers, and the farm's plot size is always 2 hectares. And it's not justified why they chose this assumption, because most of the times there have been, there's been no data, and then they just use then just another paper is cited where these numbers are given. So we didn't do that. We actually chose the true aggregates or averages in this case for the farms. So often that's just important to keep in mind. Often the differences between the approaches would be much bigger than it is outlined in this paper. So then for the assumptions, we only looked at arable farms within North Rhine-Westphalia. So North Rhine-Westphalia has about an estimate of 8,600 farms. We assumed that all farms can grow the same crops. So this is just a theoretical assumption of to show the difference between the two approaches. We used a 5-year average of regional prices and yields. So the prices and yields were available on the NUTS 2 level. That means district government level. So for our region, that would be Cologne. What else are there? Also, there is Detmold, I think, is another one. And so there's basically 4 district governments in North Rhine-Westphalia. And actually, in a later approach, we also tried to get the yield on a plot-specific level with a different approach. Then we used the variable machine cost and adjusted those for the field size and farm to field distance, which we did in a paper of my colleague Julia Heinrichs. You can have a look there if you're interested interested in how that was done. And the field specific yields are derived via the soil quality. So on that, just in short, how is that done? We use the average wheat yield from the statistics offices. So we said, for instance, for a region, here, this is the Detmold region, the average wheat yield is 80, or like between 2016 and 2020 was 82.8 decitons per hectare. So then we looked of the soil qualities of all the plots where wheat was cultivated in that time frame. So in the years between 2016 and 2020. So those are the plots, and we see quite heterogeneous soil qualities here. And then we basically just made a very simple linear regression to estimate yield functions, so that on average for the whole region of the wheat plots, we still get these 82.8 decitons per hectare, but we also can get a derived yield, plot-specific yield. So basically that way we can really estimate if you really grow wheat on a very bad field, it just doesn't give also the same 82.8 decitons, but gives us less yield. So that was our idea. Because obviously lacking actual high resolution yield data, which is rarely available, unfortunately, in Germany, and especially not available on a for like the whole country or for even whole regions. Usually it's just available for single farms or single plots. So then looking at the results, what we found is that, like looking especially at the aggregate on the one hand and the single plot approach, we found that there's in a majority of times there were little differences between the share of the crop shares, but in some cases there were more extreme differences. And what is interesting to see, or what is kind of also somewhat making sense, is that the majority of the farms where we have very little differences is farms that either are, that's very interesting to see, like 50% of the farms have 10 or less plots. So those are often, it's a little difficult to find that out, but there's there is kind of the assumption that many of these farms are not really farms, but rather renting out their land, but they're still applying for the subsidy. So that's legal. But that gives us the issue that for these farms, some of them even just have one plot. And then obviously there's no difference between the aggregate and the single plot approach. So, but this is absolutely impossible for us to distinguish between whether a farm is a real farm or just a small farm, or if it's really just somebody who's renting out land and that person is actually a lawyer in real life and doesn't care for like agricultural prices at all. So that's very difficult. So, and the same goes for the difference in the total gross margins. So we see there is on average, we see there's very little difference, but we have quite a wide distribution. And especially if you look at those, let's say 200 euro per hectare difference, that can be quite a lot of money if you scale it up to a larger farm. So just because of the methodological differences on how we actually use the bioeconomic models. So like 65%, an estimate of 65% had a difference of like where the total gross margin was lower in the single plot approach, and that's a big issue what we have with farm policy evaluation studies, where we like if the policy evaluation studies using aggregate approach finds out, oh, there's a new policy, let's say that forbids the use of pesticides and herbicides, and we find with our model there's almost no difference in the profits. But if you now use the single plot approach, you see, oh, all of a sudden there's quite a big difference in profits that leads to a whole different conclusion in the policy evaluation. So that's kind of, showing the different, or the distribution gives us a better idea what kind of farms are affected, and some might be affected pretty heavily, which in using aggregate approach in the modeling wouldn't ever tell you this result. All right, so and then just looking at the differences in the crop shares. So that's there's a lower influence on when we look at the whole farm population, but there's a greater variance in the influence of the total contribution margin and working time requirements. So the assumption of like if we actually aggregate the plots or if we look at single plots does have an influence. And our conclusion for that was simulating decision on the individual plots is of particular relevance for decision support, obviously, because for a farmer, if you just tell them, hey, you should grow 50 hectares of wheat, and the farmer says, okay, that doesn't tell me where, I have 100 plots, I could grow it here, 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 or there, so it's not really helping that farmer. And also technology impact assessment with a focus on the variance within a population. So in the PhenoRob context, if we're looking at, let's say, banning herbicides or pesticides, it could be very interesting to see which particular farm is affected. And even if the average farm, let's say, has an effect of €0, it could still be that, some farm is highly profiting from it. Some other is losing very much, and it can be very interesting for policymakers to see which kind of farms or which kind of type of farms are affected here. So in total, summary and conclusion. So we have the crop rotation, or it should be decisions, so not EUS, but DSS developed as part of the dissertation. So that allows farm-specific optimization on a single plot level. As Francisco already said, so I was really happy when that was awarded with the German agribusiness sponsorship in 2021. So that was kind of nice to see that the agribusiness society was thinking, okay, that could be a nice tool also to see in future technologies, like farms could now say, okay, if I grow sugar beets with a robot, how does that affect my farm's profitability? So that's why also the agribusiness was kind of interested in that development. And we're now currently, that's been ongoing for more than a year now. We've been talking to the Chamber of Agriculture. They're interested in putting Fruchtfolge in their advisory structure. They're actually using already the fertilization optimization part, so just a very small part of what Fruchtfolge does. So that's already implemented, but we're looking into to add more details of that. So then the development of the high resolution farm population. So that allows modeling of new technologies and policies and various models. Very happy to announce that, I think it was last week, Lin Mei Shang's paper, where Hugo and I also have been co-authors, and also Thomas Heckley, that was published, and we used some of the data that was generated there. So that was really nice that we actually got that paper in the PhenoRob context published. And we're in the future trying to look to transfer that methodology also to other regions, to maybe even create a farm population for whole of Germany. And then the analysis on the influence of the level of detail of the cultivation decision. So that highlights just the need for crop-specific modeling of the cropping decision, both for DSS and maybe also in some cases for policy evaluation. And the research outlook is, as I already said, Fruchtfolge, where we want to do a larger scale survey with farmers to see what kind of features are more needed, or is that tool too complex? Should we basically boil it down to some more things? So that's something we want to do. And also from a theoretical point, it's for us very interesting. Why do farmers deviate from the theoretical optimal solution? So what are the reasons there? Is there some things in the economics that we don't consider correctly? Are there some soft factors we're not considering? So that's I think some very interesting aspect there. And then for the further development of the farm population, I already said, we are looking to find options to do that for the whole of Germany. Also consider newer, better data sources, obviously, and extend that approach for estimating specific yields, which is also, that's why I'm highly interested in all of your guys' work, where you're looking at with drone imagery or even satellite imagery, trying to predict yields. So that's very interesting also for our work. So that's why I'm really interested in collaborating there and learning also about what you guys do. Thank you very much for your time. So that's now the end of my talk, and looking forward for the discussion.